In this video, I'm going to talk a little bit about introduction to cyclic alkanes. Now, before talking about cyclic alkanes, we should revisit acyclic alkanes because that should be something that we should have done before this topic. So for acyclic alkanes, the formula was CnH2n plus 2. That's how you calculate the molecular formula of acyclic alkanes. Acyclic would mean something that is not in a cycle, something that is not a ring. So what is N? N is the number of carbons. So if we know the number of carbons, we can multiply the number of carbons by 2, add 2 more, and that would be the total number of hydrogens for that molecule. The formula for cyclic alkanes is CnH2n. So there are 2 less hydrogens than its corresponding acyclic form. So keeping the number of carbons the same, if you were to make an acyclic alkane, you would need 2 times the number of carbons plus 2 more hydrogens. If you were to make the cyclic form of the molecule, you would just need 2 times the number of hydrogens. And we would look into this. So for comparison, we could use propane and cyclopropane, which is the cyclic version of this molecule, still with 3 carbons. So propane had 3 carbons, cyclopropane, see this part of the name? Cyclopropane still has 3 carbons, but this is the cyclic version of the molecule. Now let's look at molecular formula to begin with. So I know the number of carbons should be 3. If the number of carbons is 3, number of hydrogens should be H 2 times 3 plus 2. And that should be C3H8. For cyclopropane, again, I should have 3 carbons. The number of hydrogens this time should be 2 times 3. That's it. So carbon 3, and then the number of hydrogens must be 6. Let's look at the complete structure of both of these molecules, and things would start making a little more sense. Complete structure. Now, I have 3 carbons. Each of these carbons satisfy octet rule. So the first one should have 3 more bonds with the hydrogens. The second one should have 2 more bonds with the hydrogens. And then the third one should again have 3 more bonds with hydrogens. So that is a total of 3 plus 2, 5, plus 3, 8. For cyclopropane, I'm just going to take the first carbon and the last carbon and try to join them together. So let me show you with the model first, and then we would draw this out. I have this model of 3 carbons. Each carbon on the end has 3 hydrogens attached to it. The middle carbon has 2 hydrogens attached to it. Now, if I wanted to join these 2 carbons together, I would have to make one bond, one open bond, one available bond for each of these carbons. So what I can do is I can pluck off a hydrogen from this. I can pluck off another hydrogen from here, and that is how another space becomes available. Now, I could just take out a bond. So this is a new bond that's still available to bond with something else, and that something else is going to be the other carbon. So I would bring in this carbon, and this ring is very strange, so it's a little hard to attach, and I can join these 2 together. There is your cyclopropane molecule. So now each carbon, these were the 2 carbons I had joined. Instead of 3 hydrogens, they just have 2, because that third position is now a bond with the adjacent carbon. This has 2, this has 2, this also has 2. So I could draw carbon, a carbon in the center. This is the other carbon. Imagine these to be the carbons that I had put in boxes. The middle carbon, I can put that in a circle so that you can follow along. I did not do any changes to that carbon. So this carbon has 2 bonds. The side carbons lost 1 hydrogen each, and that's how they made space for the other carbon to come in. So each of these carbons now just has 2 hydrogens. So the molecular formula for this form is C3, 1, 2, 3, 4, 5, 6 hydrogens. So CnH2n. If you were to draw the condensed structure, you can draw organic molecules in different forms. And I have a video that I had done previously that talks about mainly acyclic molecules, drawing acyclic molecules. So the other way to draw these molecules would be to draw their condensed structure. For the condensed structure of the acyclic version, we would stop at each of these carbons and draw what is around them. So the first one is a CH3, next is a CH2, and then again a CH3. You could also draw the carbon-carbon bonds in between. For the cyclic version, please do not break up the ring. That is the most common mistake I have seen students make. They just break up the ring. You have to still show me that there is a ring. So what I can do is I can merge up the carbons and hydrogens together, but still keep the ring. So there are 3 sets of these CH2s and they are joined together. So I would still have to show the CH2s. I cannot go from that structure to drawing it this way. So you cannot draw CH2, CH2, CH2 in a line and not show that the first and the last CH2s are joined together. You would need to show that. The last way of drawing this molecule would be showing its line angle formula, which also goes by the name of skeletal formula. So I'll just write it here again. Skeletal formula. And I have again, a previous video that I have talked about all of these structures for acyclic compounds. The line angle formula for the first one can just be 1 carbon, 2nd carbon, 3rd carbon, or you could have done 1st carbon, 2nd carbon, 3rd carbon. So that zigzag line showing that these are all carbons, the point of intersection, the beginning and the end of each line is a carbon. And line angle formula does not require you to show the carbon-hydrogen bonds, but they are still there. For the cyclopropane, it is just a triangle. So you do not need to mark the carbons. The beginning and the end of each line is understood to be a carbon, and then the hydrogens don't need to be shown. But again, if there is a heteroatom like an oxygen or a nitrogen, a sulfur, a phosphorus, all of those need to be shown, and hydrogens attached to those also need to be shown. The video I keep talking about that, again, has examples of those. We can do one more. We can do a cyclobutane and a butane, which would be 1 level up from what we just did. So we could do a butane cyclobutane comparison. We know butane should be 4 carbons long. Let's start with the molecular formula. So I have a C4. According to the general formula for acyclic alkanes, I should have 4 times 2 plus 2 more hydrogens. So that should be a total of C4H. 4 times 2 is 8, plus 2 more is 10. For the cyclic version, for the ring version of 4 carbons, I should still have 4 carbons, but the number of hydrogens this time should just be 2 times 4. So C4H8 should be the molecular formula for cyclobutane. Let's start with complete structure. complete structure requires you to draw all the bonds. So I have 1, 2, 3, and 4 carbons. The first carbon can have 3 more bonds, the second one 2 more, third one 2 more, and then the last one could have again 3 more bonds. And each of these bonds would be with a hydrogen, because these are simple alkanes. I don't have anything else in them. So those are the 4 carbons. C4 hydrogens would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So our molecular formula makes sense. Now, if I were to draw the complete structure of a cyclobutane, I would have to join the first carbon and the last carbon together. Again, the same thing that we did before. I have a cyclobutane. I am going to remove 1 hydrogen from the first carbon, and I would be removing another hydrogen from the last carbon, and that's how I would make space between these 2 carbons to form a bond. So I made these 2 carbons, and there is my bond. Now I hope you realized that I struggled a little more when I was making this ring. It was a little harder to attach these in the first ring. Remember, these rings, the carbons are all tetrahedral, so their ideal bond angle is 109. But you are kind of squeezing them to a much smaller bond angle. So the smaller the ring, the more strained it is. And in a later video, I'm going to talk about 5-membered and 6-membered rings like a cyclopentane and a cyclohexane. And you would see that those are the rings that have the best kind of angles that you can probably think of. All the other ones, like the 3-membered, 4-membered, 7-membered, 8-membered, these are under a lot of stress. The smaller rings are kind of squeezed to a much more compressed bond angle. And the larger rings, like 7 and up, those are a little more widely spread bond angles. So either of those are not the best type of rings when you do a chemical reaction to make them. So here is my cyclobutane ring. I have 4 of these carbons. These 2, I had removed 1 hydrogen each to make space for this carbon-carbon bond to form. So you can see each of these carbons now have 2 hydrogens. So 2 here, 2 here, 2 more here, and then 2 more here, which is a total of C4H8. So to draw this, we would basically draw a square. Let's say this and this were the carbons that I joined together. Now each of these carbons have 2 hydrogens. And these originally had 2 hydrogens to begin with. So I could put these in circles. So those are my ones in circles, which originally also had 2 carbons to begin with. That's the complete structure. If I were to draw the condensed structure, then I would have to write CH3, CH2, CH2, and another CH3 for butane. And for cyclobutane, again, keep the cyclic version of the molecule intact and write down what is with your carbons. So CH2, CH2, another CH2, and a 4th CH2, and these 2 join together. But now it's in the form of a cyclic molecule or a ring. And then the last one would be my skeletal structure for this molecule. For the first one, it's a zigzag. So 1 carbon down, up, or you could have started up, down, and down. Each of these positions, the ends of each of those lines is a carbon. And I did not need to show the carbon-hydrogen bonds. For the other one, I will just draw a square. Not mark the carbons. Again, it's understood. These positions are all carbons, and then there must be hydrogens. You do not need to show them, but they are there. For practice, you could play around with trying to draw cyclopentane and cyclohexane. You could do it the same way, draw a pentane and then make a cyclopentane from that, draw a hexane and then make a cyclohexane from that. And then you can let me know in comments if you struggled with any portion of it or have questions about it, and I would be happy to answer. Thank you.